All right, we're going to do lesson 5.3, which is optimization of exponential functions. So when we did optimizations, we had some kind of algorithm for it, and this is kind of basically the steps we used in the previous algorithm. We're going to try and stick to as much as possible. So instead of wasting time going over all the steps you can read for yourself, I'm going to jump right into an example. So in the first example, it says determine the absolute maximum and minimum value for the function f of x between -4 and 4 inclusive. So I think the best thing to do here is try and figure out what the graph's going to look like. So what I'm going to do is I'm going to say that I'm going to find my x-intercept. So we're going to say that f of x is equal to 0 when, and if we look at it carefully, the only way that's going to equal to 0, we know that e to the negative 2x never goes to 0, so that means it's going to be the x in the bracket that's going to set it. So when x is equal to -2. So we also know that our y-intercept is when we let x equal to 0. So we get, in this case here, if we let it x equal to 0 on the exponent, that's going to be 1. And in the bracket, when we let x equal 0, that's going to be 2. So it's going to be when it's 0 and 2. So I'm going to put that there, and that's going to be my 2, 4, 6, 8, 10. And this, the horizontal scales are already labeled for us. We have our y-intercept already plotted. Now I can start with my calculation for my derivative. So I'm going to take my first derivative of the function, and the way it's going to work is I'm going to take derivative of what's inside the bracket, which is basically going to be just 1 times e to the -2x, and then we're going to add it to x plus 2, right, times derivative of e to the 2x, which is e to -2x, times derivative of -2x, which is going to be -2. We can clean this all up a little bit, see what it looks like. What can I factor out? I can factor out e to -2x. There it is. Let's see if that helps out. So we have f prime of x, which is equal to e to the -2x. And then we have 1 left over there. And we multiply the -2 back. So it's going to be -2 minus 4. Or we have f prime of x is equal to e to the exponent -2x. And then we have -2x minus 3. And we have to set that equal to 0, right? But what I'm going to do is one more thing. I'm going to factor out the negative, just to make my life a little bit easier, right? We don't have to do this, but I want to factor out the negative there. So we're going to have f prime of x is equal to negative e to -2x, and we have 2x plus 3. So f prime of 0, f prime of x is equal to 0 when we have negative e to -2x equals 0, which never happens, does not exist. And we're going to have it when 2x plus 3, that's supposed to be a 3, is equal to 0, or x is equal to -3 over 2. So it's going to be at -3 over 2. If I were to solve for, kind of squishy in here, f of -3 over 2, what we're going to get is equal to -3 over 2 plus 2 times e to -2, -3 over 2. The 2's will cancel out. The two negatives on the exponent also become positive, so it's going to be e to exponent 3. So that means f of -3 over 2, -3 halves over 4 over 2 is going to give me 1/2. I'm going to have e to exponent of 3. Simplifying a little bit more so we can see it all polished. We're going to get e to the exponent 3, e to the exponent 3 over 2, which is approximately equal to, let's put my calculator, 10.04. And we have to test our n values. So we're going to do the same activity. So we're going to have f of -4. All right. So -4 plus 2 is going to be 2. -2, sorry. And then we're going to put the negative in for the top. We're going to have e to the exponent 8, which is approximately equal to -5.962. And we're going to have f of 4, which if we plug in 4, we're going to have 6e to the negative 8, which is approximately equal to 0.002. So we can see in this case here that this value here will be our max. This will be a minimum point, and that will be a minimum point. If I were to sketch out the curve, we have an x-intercept, which was negative 2, which I forgot to put in the beginning. We have our maximum point, which is negative 3 halves and 10.04, so it's slightly off. Negative, so it's slightly off the chart. And then we can see that when we go to f of 4, it's approaching 0.002, and that makes sense because, well, let's draw the sketch and see what it looks like. It will go up until it hits the maximum, come back down until it hits the intercept. Somehow it's going to turn, and then it's going to go down close to the function. Okay, that looks like it looks right. We could actually put that into Desmos or some other kind of graphing software to actually check to see if our graph looks correct. For example number 2, we've got to read the question carefully, and it's talking about revenue in hundreds of units, and the capacity plant is 800 units. So really what that's telling us is that when we're looking at this part over here, we know that we have to look at when the plant makes no units all the way up to 8 units, because it's in hundreds of units when we'll plug it back in. So again, this is calculus. We always have to take the derivative for this part here. So what I'm going to do is I'm going to take the derivative of r, my revenue function, and let's take it nice and slow. So we're going to take the derivative of 40. There's 2 ways of doing it. I can take out the 40, treat it as a constant, take the derivative of everything else in front of it. But if I take out the 40, what's going to happen is with the 30, I'm going to have a decimal or a fraction, 3/4. It's okay, but I'm going to try and avoid that. So I'm going to keep the whole entire function the way it is. So dropping the 2 from the x squared, I'm going to get 80x. So derivative first times the second, so e to the negative 0.4x, right? Then I'm going to add it to our 40x squared times derivative of e to negative 0.4x is e to negative 0.4x times the derivative of the exponent, which would be negative 0.4, and we have the constant which take the derivative. If it goes to 0, I don't have to worry about that. We always look for something that we can simplify. Before we simplify it, I'm going to multiply it all out. So we get r prime of x, which is going to be the 80x e to negative 0.4x, which was boring. Multiply the negative 0.4 with the 40. We're going to get negative 16 x squared e to the negative 0.4x. Now we can actually factor something out. Again, 16 times 5 gives me 80, so I know I can take out 16 from both the 80, oops, that wasn't a highlighter, from the 80 and the 16. We can actually factor out the exponent as well, and we can factor out an x. So when we do this, that's what it looks like. We're going to factor out a 16x e to the negative 0.4x, and we're left with, on the first part, just 5, and the second part, we're left with x. We know that r prime of x is equal to 0 when we have 16x e to the negative 0.4x equal to 0, and the exponent never goes to 0, makes the base go to 0, so that's not going to be the solution. But the x on this part over here can be 0, so we know that this is going to be the case when x is equal to 0. On the other side, we have 5 minus x is equal to 0, or x is just simply equal to 5. So the next thing I'm going to do is I'm going to plug it back into the function. So I'm going to say f of 0. So if I make x equal to 0, the e to the exponent is going to go to 1. The 40x squared, that's going to go to 0. So basically that's going to go to 30. If I do f of 5, now we're going to do a little bit of work. We're going to have 40 times 5 to the exponent of 2 e to the negative 0.4 times 5 plus 30. And when I do that, it's going to give me a decimal, so I'm not going to worry about exact numbers for this part here. It's going to be 165.33. And then we have to do one more, right? We still have to do the f of 8. And the reason we have to do f of 8 is because the capacity of this facility could only do 800 units, and the units are in hundreds, so that means we have to divide it by 8. So I have to do f of 8. And if I do that, we're going to have our 40 times 8 to the exponent 2, e to the negative 0.4 times 8. Punch that into my calculator. Again, we get a decimal, and I get 134.35. So if we compare our values, right, if we compare our values, I'll just highlight a different color. We have 30, we have 165, and we have 134. That means that in this case here, our 30 is going to be a minimum. Our 165 is going to be a maximum. And our, if you want to think about this as well, is going to be a minimum. So if I read the question, it wants a maximum. So if it wants a maximum, we can therefore say, just recall, revenue is in thousands. So if it's in thousands, we can say therefore the max revenue is approximately, it's approximately because I didn't carry all the decimal places, right? Approximately $165,330 when, and again, 500 units are sold, because the units are in hundreds. For the next one, we have a prescription drug is injected into a body such that the concentration of the bloodstream is given away after so many hours, at which time is the highest concentration occur in the first 5 hours. So if you think about medication, the way it works is you take a pill or you get injected with it, it builds up in your bloodstream, so the potency or the concentration is going up. And as it's going up, also your body's consuming it. So it's going to go up to a certain point, to a maximum, and then your body's going to consume it coming right back down. Okay, so let's keep that in mind. And again, when we have 5 hours, right, we care about the first 5 hours, we know that the concentration will be 0 at 0 most likely, unless you have some trace from before, and we're going to carry up to 5 hours. So 0 to 5 hours. Okay, so let's take our derivative. So we have C prime of t. C prime of t is going to be, well, this time I'm going to leave the 10 out of the calculation, right? And if I do that, the derivative of e to the exponent of negative 2t is going to be e to the exponent of negative 2t times derivative of the exponent, which is negative 2. And we have the operation. Derivative of e to the negative 3t is going to be e to the negative 3t times derivative of the exponent, which is going to be negative 3. I'm using square brackets here so you can visualize the difference between the two. So let's clean this all up. So my 10 is a constant, still leaving it out. And I'm going to have negative 2 e to the negative 2t. The two signs change. Okay, we have a negative times another negative, which is a positive. So we have 3 e to negative 3t. I'm going to factor out e to negative 3t. I'm going to simplify this a little bit. So when I simplify this, what we're going to get is C prime of t is equal to 10 times negative 2 e to negative 2t plus 3 e to negative 3t. I'm going to factor out e to negative 3t, and we have to be pretty confident with our exponent laws. So when I do that, we're going to have our 10, and over here we're going to have our negative 2 e to the exponent t plus 3. I can actually factor out another negative. So if you're wondering about I'm jumping all over the place, but if you're wondering what I'm doing with the factoring of the exponents, if we have the exponent negative 2t, and I have an exponent of negative 3t, the operation, right? The operation says what we're going to do is when we divide exponents, we subtract. So that means we're going to have negative 2t subtract negative 3t, which gives me t. Okay, and I can leave it like that, or I can turn it around. It doesn't make a difference. We know that c prime of t is equal to 0, 1, while the 10 doesn't do anything for me. So that means it has to be the negative 2e to the t plus 3 has to be equal to 0, or 2e to the t is equal to 3. I already know some space, so I'm going to go over here. And if we solve for this, then we're going to get e to the t is equal to 3/2. We're going to use logs or lns, but in this case here, we know that the inverse of e is going to be ln. So when I do that, I'm going to take the ln of e, I'm going to drop the exponent, and whatever I do to one side, I take to the other. So I have the ln of 3/2. So our t in essence is going to be equal to ln of 3 over 2 divided by ln of e, which ln of e is 1. So if I were to put ln of 3/2 into our calculator, we get t is equal to approximately 0.4055. So since it's we're testing to see what the highest concentration is, we have to test at 0.4055 and 5 for t. So if we do t of 0, that means we have 10 times e to the negative 2 times 0 minus e to the negative 3 times 0. That means this here goes to 1. That there goes to 1, which 1 minus 1 is going to be 0. So we know that our t of 0 is equal to 1. Maybe I should have wrote a little bit smaller. Or you know what, just to save some space, I'm going to put it here at the end. We have to test our middle value. And I'm not going to rewrite it all out. I don't have the space for it. I don't have the space for it. So all I would do is replace the t with 0.4055. And when I do that, I'm going to get approximately 1.4815. And if I do t exponent 5, we have 10. I can fit that one in. Negative 2 times 5 minus e negative 3 times 5. Put that into our calculator, and we get T5 is equal to approximately 0.00045510. So if that's the case, we want to know when it's the highest concentration. So the highest concentration will be when here. So this will be our, this will be our max. And it makes sense that this is our min. Assuming that we haven't taken the drug ever before, there should be 0 concentration in our bloodstream. And then 5 hours later, it's dissipated. So that also would be a min. So I don't have room for the therefore statement. So therefore, put it here, highest concentration. That's horrible. Therefore, I'll put it at the bottom. Therefore, highest concentration will occur 0.4055 hours, or approximately 24.3 minutes. one last question. It's really a complicated question because there's all kinds of things going on there. So the radial probability density, it says for n equals 2 and L equals 1, M equals 0. For the hydrogen atom can be written as P of R. All I care is that C is a constant. A is that value there. It says find the most likely position R of the electron, i.e. find the radius of R at its maximum. So we know it's going to be some kind of maximum. All right, so let's see what we have to do here. Keep that all in mind. So let me write the function down again. So we know that C is a constant, right? And we have R to the exponent 4, e to the negative R over A. I'm not going to plug in A right now because A is a constant. So if I take the derivative of A, it's going to go to 0. It's going to disappear anyway. So let's see what happens with that. So if I do P prime of R, we have our constant, which we're going to take out. The derivative of R to the exponent 4 is 4R cubed times the second part, plus we have R to the exponent 4 times the derivative of the exponential with base e, which is itself, times the derivative of the exponent, times the derivative of this part here. So this is where we have to be careful. So it's going to be negative 1 over A. Let's clean this all up. C is still a constant. I'm going to leave it out. And then, what can we factor out? We can factor out that. Okay, just we can factor out an R to the exponent 3. We can factor out the e to the exponent all over A. So if I do that, what we're going to get, take it out. So we're going to take out R to the exponent 3, e to negative R over A. And what we're left with is, on the first part is 4. On the second part, it's going to be minus R over A. All right, so we always set it to 0. And that happens when we have C R to the exponent 3 e to the negative R over A is equal to 0. And, or, doesn't make a difference, 4 minus R over A is equal to 0. So for the first one, anything we put for the exponent will never set it equal to 0. So it's going to mean that's R is equal to 0. And for the second part, if I want in terms of R, that means I'm going to say that 4 is equal to R over A. I want to get rid of the A, so we're going to have R is equal to 4A. And now I can plug in the A value for R if I want to, right? So we want to see if it's a max or a min and when. So let's plug in the values. So we have P of 0. So P of 0, going back to my original function, if I plug in an R there, everything goes to 0. If I do P of 4A, and again I replace A with 0.529 times 10 to the negative 10, put that in my calculator, we're going to get 3.67 times 10 to the negative 41 C, because there's a constant C. And even though the point at 4A is really, really, really small, we know that this is going to be our max, and this is going to be our min. If I go back to the question, I'm looking for something else. Let's see if it's bounded. It's not bounded, so that means we have our solution. So we can say, therefore, most likely radius for hydrogen atom will be at about 3.67 times 10 to negative 41 C units. I'm not sure what the units are, so I'm just going to put units. And that's all for now.